the way the algorithm is set up, it takes order of n squared time because we have order of n states over here, right? So we have a state corresponding to each of the positions in the string. So we have order of n states, plus in each state you have possibly n positions in the position set. So for instance, out here you see there are 4, and in general the only bound you can give to the number of positions here is n, and then you have to look at what are the following positions from each of those n. So that means that constructing each of these states might require order n time. So easily you can see order of n squared time complexity, right? So we would like to see if that can be improved. Okay, and that's exactly what we are going to do. Okay, how do we improve the size? We would also secondarily look for improvements to the way we represent transitions. Okay, so we said that transitions in general you need to use hash tables and so on, which is not that efficient. And particular case, we see that the number of transitions out of each state is quite small, and we would like to see if there is a faster implementation. Okay, so both of those we are going to try to do by looking at this general algorithm and trying to observe the structure of what it produces and seeing whether it's possible to improve further. Okay, so as we said, the DFA that's constructed by this algorithm, it has a linear structure. Okay, and essentially there are states, and the states sequentially they correspond to the positions within the string, right? Because there is no, it's a simple string, so you're going to, your positions, you're just going to advance left to right, and you're never going to come back to the beginning, right? So you just go forward. So corresponding to moving forward through this string, you will have states. So the nth state here will correspond to the nth position within the string, right? So it's a very simple structure, okay? And so that's a linear structure. So let's say something a little bit more specific. So let's number these states from 1 to n plus 1, right? So obviously we have n plus 1 positions here, right? Starting from 0, going all the way to n. So n plus 1 positions, so there will be n plus 1 states, okay? And the state I is reached on matching a prefix p of 1 to I minus 1, right? Again, very simple because the, say for instance, this state, 0, 1, 2, 3, corresponds to being over here, right? After having seen the 2 A's, right? So you are in this position, and so since you have seen the first 2 positions, your position set is going to include the next position you're going to see, which is 3, right? So that's going to be the largest thing, because obviously if any larger one is included, that means you have already gone further forward, right? So therefore, the largest element of p set in the ith state is going to be just I. Okay? Now, there's one more thing we can say, okay, which is actually very important. And let's say we are in state I, okay, in state I, which means that we have so far seen matched symbols corresponding to the first I minus 1 positions of the pattern, right? So if you have in state I, you have seen I minus 1, right? You have made I minus 1 transitions, you have seen I minus 1 symbols, okay? And of course, if you are thinking about matching against a subject, that means these I minus 1 positions should match the last I minus 1 positions of the subject string. Okay, so let's say we have so let's say we have something like this. Okay, let's say this is our S, okay, and our P is of course given there, A, B, A, and let's say we are at this state, okay, which means that we have seen the first 4 symbols, right? AABA, okay? And so let's say we are, okay, so this is how far we have gone on the subject string, right? So we start with subject. So if you think about how the matching is going to go, you're going to start from here and then you're going to scan the symbols in the subject string one by one, okay? So let's consider the instance where the cursor is here and, you know, at this point you will be in this state, okay? Because you can see that AABA is going to put you in that state. Okay, and you can see that, well, this AB is not going to help you do anything, right? Because the pattern doesn't start with the AB, so that's not going to help you, so you will have only gone this far, right? And then okay, so this is where we are. Okay, so now the point to see is that we have matched so when we are in this state, okay, so we have so far matched, again, the highest position is 5, which means that we have seen up to 4 symbols, okay. So these 4 symbols match the last 4 symbols of the subject, okay. And the other point to remember is that we have in this automaton, or in the regular expression, we have a sigma star at the beginning, right? So if you think about how, given this ABA could be matched, okay? So one way is, okay, you just go from, you don't match anything against sigma star, and the entire ABA matches part of the pattern, okay? So that is how you get to this state, right? So it's also possible that some of this AABA was matched off against the sigma star, and only the rest are really a match for P, okay? So, as an example, you see that we could have matched this part against sigma star and just this part against P. Okay? If we did that, then we would have made only one transition in the automaton, and we would have reached state 2, right? And so that is why state 2 is included here, right? Because you can't tell for sure whether this AAB was matching for these characters from P, or maybe, you know, it should be a match. They should be matched off against sigma star, right? Once again, the DFA is always trying to keep track of all possible matches. So that's why it's saying, okay, I could be having a match up to 5, or I could be having a match up to 2, or in the worst case, the entire thing is matching against sigma star and I haven't made any progress at all, right? That means I'm in the initial state, which is why I have 0, 1 over here, right? So this is the way we understand how these symbols came about. Of course, we could understand them by simply, blindly following the McNaught and Yamada construction. We would end up with that. But we are trying to have a different understanding that allows us to improve the algorithm. Okay? So in particular, what's going to happen is that whenever there is a suffix over here, okay, that matches a prefix, then you have the possibility that let's take this suffix. Okay? If this suffix matches a prefix, that means we could have basically matched all of this against sigma star and then only matched this against P. Okay? So as a result, whenever there is a suffix of the pattern that we have seen so far, that's also a prefix, then each of those prefix positions will also be included in this set. Okay, so 5, up to 5, you take this and then you look for suffixes of this that are prefixes. There's actually one and one suffix of length 1 and one suffix of length 0, right? There are also prefixes of this. So in all of those will appear here. Okay? So this is the crucial part of the structure that helps us make things improve the automaton in one way. In particular, what we are saying is that all these positions that appear are purely a function of this, right? Once I have this file, I can immediately say what prefixes and what suffixes and so on, and I can immediately derive everything else once I have the largest position. Okay, and I also know what the largest position is, which is, from the state number, that is the largest position. Okay, so now I know that. So what I'm going to do now is, instead of remembering all these, order of n positions over here, I'm going to remember just two. I'm going to remember the largest one and the next largest one. Okay? So the idea is that if I want this one, then I can simply go to the position which has 2 as the highest thing, and I can ask, what is your predecessor, right? So instead of storing everything here, I can just go back to the state label 2, and then I can say, okay, what are your predecessors, and I can just pick it up. Okay? So this is the key idea that we're going to use. Instead of representing all the positions, possible positions right here in the state, we are going to say, let's just have some sort of a link back to the previous state. That is, this state will have some sort of a link to state number 2, and whenever we need any of these, we'll just go to that position and pick it up from there. So we're just going to rely on a linking step in order to avoid computing all of this. And why does that happen? Well, we said the reason why this algorithm takes n squared time to construct is because you have order of n things here, right? So if I replace the order of n things by just 2, then, well, I have an order of n algorithm to construct the automata, right? Because the order of n factor at each state has been eliminated, right? So that's why we want to use this structure to eliminate some of the states that we can, obtain by walking back. So this is what we're going to do. Okay. So again, it states the same thing. Remember only the largest j less than I. Okay. So we're going to remember the state itself says what the largest position is. We're simply going to remember one more thing. Okay. And that is going to be what we're going to remember. And then we are going to add what are called failure links, so that from state 5 we can follow the failure link to state 2 in order to pick up what are the other prefixes that are relevant. Okay, so we are going to rely on that linking structure. Okay, and as I said, if you have only 2 positions per set, then the algorithm becomes faster. Okay, so now, let's say we do that, and we end up with what is called the Knuth, Morris, and Pratt automaton for doing this, solving this problem. Okay, and so this is the automaton we constructed using the McNaughton-Emott algorithm, and this automaton for the KMP automaton is basically you get here by essentially doing what I just said. For each of these states, you remove all but the last 2 positions. Okay, so that's how you get all this, right? So that is the first step we have done. Okay. And the second thing we're going to do is we're going to say, you know what? I'm not going to have a complex or arbitrary structure for the transitions. I'm going to say you can either go forward or you can follow the failure link. Okay, so those are the only 2 options I'm going to give you, and that's going to simplify my automaton by saying that each state has only 2 transitions, right? So if I say each state has only 2 transitions, then I can easily represent that using a simple structure. I don't need a hash table or anything like that. Okay, so those are the 2 things I've done to go from here to here. So just chop off everything except the first 2. Everything except the last 2, and then I said, okay, I'm not going to have all these links on B and so on. All I'm going to say is that I'm going to either allow myself to go forward. If I can't go forward, so what does this mean? Okay, so let's try to understand that more clearly, what these transitions are doing. Okay, so let's say we look at this position, like this state. Okay, so that means you have matched either up to position 2 or position 5. Okay, so let's write down the, okay, I'm still have the things over here. Okay, so, right? So, if we are at this position, okay, what that means is we have either matched up to here in the pattern, or we have matched up to here in the pattern, right? Okay, so how do we decide what is the forward transition from the state? Okay, let's say for the moment assume it doesn't even exist, we are trying to construct. So we are at state 2, 5, which means that we are either here or there. Okay? So how do we, what is the forward transition? Well, the forward transition is always going to be the one that extends the longest match. Okay, so the forward transition is going to be on B. Okay, so we're going to have a transition on B, and that's pretty obvious because the forward transition simply spell out the pattern itself, right? So that's obvious. The question really is, what happens for the other pattern, for the other match, right? The other match is up to here, right? In this particular case, that match is not going to be extended on B, right? Because if you see a B, then, well, you want an A in order to extend this match further, right? So that match cannot extend. Therefore, what you need to do is, if there is no match, so that particular match cannot be extended. So when you go to this state, right, what happens is that you go to 1, 6, which basically says this match cannot proceed or fail, so basically you go back to the beginning of the pattern, right? And that's why in this case on B, you're going to 1, 6. Whereas if you look at position 1, 2, right? So position 1, 2 means you are either here or here, right? So you're before inspecting the second symbol or before inspecting anything, okay? So in this case, if you see the forward transition is going to be A because the longest match is extended on A, right? So you see this state, we are looking at this particular state, and this state on A, you can see that both of these matches can be extended on A, right? It's not just this one, because the symbols, the next symbols, if you look at this position, the next symbol is A, and if you look at this position, the next symbol is A. So both of those matches can advance, and therefore you're going to have, the next is going to be from 1, 2, you're going to go to 2, 3, right? So that's why I'm saying, the symbol at both positions, I and J are same, then on forward transition you'll go to I plus 1, J plus 1, okay? If they don't match, then I will go to I plus 1, but J, the match on J cannot continue. So you got to say, okay, I'm going to go back to my further, so again, going back to the other case, right, so we have over here and here, right? So we know that this match cannot proceed, and let's make sure that we remember that there is also the match for the empty prefix. So there are 3 matches that we have that are possible. So what we are going to say is, well, I advance this on B, but if it doesn't match B, right, then I could potentially advance this one, right? So what I'm going to do is I'm going to say, okay, whenever I cannot advance the longest match, I'm going to follow the failure link and go to that state, because I know that so far I certainly have a match up to that prefix, okay? And then I'm going to say, okay, can I make a transition from there? And that's exactly what happens here. If you can really follow all these curly edges, you will see that the 2, 5 goes back to 1, 2, right? Because we always said the failure link, remember, is always going from this one state labeled by this one to that state. Okay, so I don't even have to say draw the failure links explicitly, because this is the failure link of this. Okay, so you can see that this, well, again, if you can figure out where these things cross, well, it goes back to state 1. Right. And then similarly 7 has a link going back to state 2 and so on. Okay? And so what I'm going to do is, whenever I'm not able to extend the match for my second longest match, I'm simply going to go back to the state corresponding to second longest match, and then from there I will check if I can go forward. Okay? So this way I am able to simplify the automaton. So I have either a forward link, and then I have a failure link. So those are the only two links that I have. Okay? So that allows me to make the automaton simpler and therefore makes my checks at runtime simpler. Okay? And then let's say what I just said now. So if you can't advance the match on the current symbol, you're going back to go on the fail link. So that tells you, okay, maybe the longest match cannot be advanced, so we're going to look for the next longer match, and then we're going to try to advance that. Okay? And it's possible that cannot advance, so then again you may have to follow the failure link again. Okay? So in general, you may have to follow the failure link many times. Okay? Up to n times. Okay? So it might seem that because the number of times we follow the failure link is up to order n, that we have somehow increased the runtime, the match time. Okay? But we really haven't, at least in asymptotic terms, because you can see that for each step I go back, I must have taken a step forward, right? So I could say, I can use a clever trick called amortization. Okay, so what I can do is I can say, I'm going to think that every backward transition is free. Okay, and the way I'm going to do that is by saying I'm going to charge myself twice for going forward. Okay, so you know that I cannot go back without going forward, right? So every time, if I count going forward as 2 units of cost, then I can go back as many times as I want, and I would have already paid for that earlier, right? Because this is, it's very simple, right? You can't go back without going forward, right? So if you are stuck in state 0, then you can't follow failure links, right? So only if you are here, maybe you can go on failure link. And then you have to make some steps forward before you can go on failure link any number of times. So the point is that by essentially thinking about this property that you cannot go back without going forward, you can account for all the costs in terms of the forward transitions. And we know that forward transitions are taken on once per symbol, right? So you can say, well, so what this means is that my algorithm is not my algorithm is not making just m transitions, but in fact it may be making 2m transitions. Okay? Because I want to, the forward transition for each of them, I want to charge myself twice because I want to account for the possibility I may be going back. Okay? So as a result, we have an algorithm which whose asymptotic complexity has been increased. Okay? And even if you count exact numbers, it might have increased by a factor of 2, and in fact it doesn't even increase by a factor of 2 in practice, but at least we know that that's an upper bound. Okay? So that brings us to this algorithm called KMP, which is, interestingly enough, can be stated without really referring to any automaton structure. There are a couple of arrays that you keep, not a couple of arrays, actually one array called fail, and that's all you need to represent the automaton, and that's why it's extremely simple. I won't go through this because this is exactly what we have said so far. Although the algorithm is simple, I'm not sure it's the easiest thing to follow. Okay, so it's actually doing exactly what's in here, and this picture is easier to follow than the text there. Okay, so now the next question is, okay, so now we dealt with a simple case where we have exactly one keyword that we are trying to search in the middle of some text, right? So we have an efficient algorithm. If you are searching for a word in a document, well, that document may be very large, and in a single linear scan of the document, you have searched for this string. Okay, so that's what you have been able to do. But in general, you would be searching for one keyword, right? Typically, you might be looking for one of n keywords. And the question is, okay, so can we take this KMP algorithm and generalize it so that it will solve, multi-word or multi-pattern search with the same degree of efficiency? Okay. And of course, so the answer is it can be done, and the resulting automaton is called Aho-Karasik automaton. And as it turns out, this algorithm was published before the Knuth-Moritz-Pratt algorithm. Okay, a few years before, but somehow I don't think the ideas themselves were happened before, but I think basically the KMP algorithm was not written up for a few years after the Aho-Karasik algorithm. Okay, so what does it look like? So basically, KMP looks like you have a linear automaton, right? It's equal to states, and then you add failure links to it. Okay, so if you talk about a multi-way, multi-pattern, then the more natural thing you might expect is, okay, I'm going to have a try, and then I'm going to put failure links on tries. Okay, because if I know so why do failure links come in? If I know exactly where to start, right? Let's say if I want a match from the beginning of the subject and that's it, then I will never need to slide and go back and do all those failure link stuff, right? So I just need to do a sequential match. Same way, if I'm doing multi-pattern search, but the matches have to be at the beginning of the string, all I have is a try, right? So I'm going to just use a try and traverse the try to figure out whether whether there is a match. Okay. So now, in order to enable me to have a match not just at the beginning but at any position, that's why I'm introducing this failure link so that I can slide over some of the text, right? And then, so if I put those slide over links on the try, maybe I can get multi-pattern match. Okay, so that's the basic idea. So let's just look at the picture. There's a fair bit of text that you can go and read, but the picture is really very helpful. Okay? So we have an example which is similar to the example we used for the try, but I made a few changes. Okay? And we are using the same approach. We start with the McNaughton-Yamada algorithm for constructing this, and then we are applying the optimizations we did for arriving at KMP, right? And the optimization we applied was, we are going to have, just remember only the largest two, longest two matches. Okay, we are not going to remember anything else. Okay, so we're going to do the same trick here. So for instance, EJ here means position numbered E. The position numbered J is the longest match, and position numbered E is the second longest match. Okay. So there is one more, wrinkle here, which is that there are positions from multiple patterns. So if I give a number to every one of those positions, I'll have a large number of positions to keep track of, right? This is not a problem for an algorithm, but obviously if I want to draw it as a picture, I want to avoid too much clutter so that it'll be easier to follow. So what I've done is I have only attached labels to certain positions. What I've avoided is, for instance, if you look at the two words top, or three words top, tool, and tooth, right? So the symbol T, right, is going to be matched together for all of them, right? Which means that the T position will always occur together for all of them, right? So why give them separate numbers? Let me just give them one. Same way, if you look at the O in top, that O is always going to occur with the O in tool, the first O in tool, and the first O in tooth. So again, to avoid clutter, I just give all three of them just a single number. Okay, that's why you see numbers, some positions are missing numbers because they are essentially there. Okay. Now, the way you move forward and backward is, whatever we've said in the KMP, again continues to hold. So let's take a couple of examples to reassure ourselves. So for instance, I said the failure links will always go from this state to that state, right? So you can see that, okay, so it's going from this state with this as the highest numbered position to this as the highest numbered position. So you can see that it goes over there, right? Same way you look at here, okay, so this is state, highest position is I, and the second highest position is D. Its failure link is going to go to the state whose highest position is D. Okay, so that is how this is all. So that part of how failure links are set up is exactly the same as in the KMP algorithm. Okay, and the logic about when you go forward, okay, so you can see that from CH, right, on E, right? So let's look at what is the position C and what is the position H, right? C is a position that has contains an E, and H is also a position that contains an E, right? But notice that their prefixes don't match, so they are actually distinct instances, so they have different numbers. I couldn't have given them the same number. Okay, I could have given them the same number only if the prefixes also match. Okay, so I couldn't give them the same number, but you can see that they are the same character. Therefore, both of those matches will advance. The longest one as well as the second longest one are able to advance, and that's why we are able to go from CH to DR. Right? Now, there are cases where let's see. Okay, so here is a case, right? So this is L8. Okay, it's unfortunate. It looks like a 1-8, but it is actually L8. Okay, and L8. The 8 advances to 9, okay? But L cannot advance because if you look at what is on L is a Z, right? So the symbol at position L is Z, and obviously this is a T. So obviously that cannot advance, and the only one that can advance is, you can go to 9, and when you go to 9, well, you can also advance an earlier match, which is which you figure out by so basically this L cannot advance here, right? So what you're going to do is you're going to follow the failure link here, and so you reach that state, and you can see that that state can advance to C, okay? And so if at runtime, if you don't have a match for T, then what you will do is you'll go back and you will look for a match for Z. And then you can see that basically what it means is that you're sliding over T and saying, okay, I no longer have a match that starts with the T, but I have a match that potentially starts with O, and that's the one that I'm going to be looking for if I'm here. Okay? So again, Aho-Karasik is a simple generalization, but in fact, from a practical perspective, it's much more useful. So what you'll see is that there are many tools that continue to use Aho-Karasik algorithm, whereas KMP is essentially used as to teach courses or to understand the basic idea behind Aho-Karasik. But the algorithm itself you will generally not see being implemented in software. Any questions? Okay, so that brings us to this kind of automata-based way of doing string matching. Yes? How do you figure out you can go on 2, right? Okay, so the way to do that is you follow this, right? You know that L cannot advance on T, right? Okay, so you go to the failure link of, so what do you get? You get to this state, right? And you can see that that state cannot advance on Z, right? So you know that, okay, if at all I have a chance of extending something, then I have to go slide one more. So I go from the failure link of, follow the failure link of this, right? I go to the parent state, K, right? Well, that still doesn't have anything on T. So then I go to the failure link of that, right? So you notice that I just don't show the failure link that goes back to the start state because it's kind of obvious, right? So essentially, by following the failure link a few times, you end up at the start state, well, and the start state has a transition on T. And so that is going to be position 2, and that is the position that can advance. Okay? So the way you figure out this state is exactly by following the failure links, finding a position where you have a transition on this symbol, and that's how you get this. Right? And again, this part is not different between K and P, and how can I say? It's exactly the same. It's a good question. I was trying to explain that, but somehow I lost track of it myself. Okay. Anything else? Yeah.
Why don't we fill the second largest K?
Which state? Can you tell me?
From the start, if I take O, there is only K.
I'm sorry. Say that again.
From the start state,
Right?
if I take O,
Right?
then there is only K. There is no second largest.
Because there will be 0, right? And yeah, you're right. I did. Yeah. In the states, I've explicitly indicated 0, and for some reason, I left it out. So again, a good catch. Okay, so that should be 0K. Okay. Was there something else?
What is the benefit of moving the back into the first stage, as in the start state?
Can you figure out where all the arrows are going now?
No, as in the earlier system also we have used the back into start state. What is the benefit here? As in what is the change?
So what does it say? To reduce clutter. That's it.
But still
Right?
we are increasing the height of the tree. If we are reducing
No. I'm not saying those things are not included. The picture doesn't include that. Okay? So that's why it's called clutter, right? So clutter refers not to the, you can't remove, lines of code from your program because of clutter, right? I can only remove it from a picture that I want to use to illustrate. Okay. Anything else? Okay, very good. So that brings us to conclusion of discussion on automata-based techniques.